At the end of the previous passage, the remaining head is not enough to carry Mira over the next rise. The pump waits at the threshold. It does not create water. It transfers energy into the moving stream. At the inlet, the water gathers around the impeller eye. When the impeller turns, its curved veins guide the flow outward. The casing receives that motion and redirects it toward the discharge. A small parcel of water can now cross an elevation that gravity alone could not reach. The machine changes the route by doing work on the water, while the pipe, the particles, and the moving pressure field remain part of the same physical story.
Yet the energy entering the machine is not the same as the energy delivered to the water. Some remains in the motor as heat, some in the shaft and bearings as friction, and some in the rotating pump as vibration and sound. The useful question is not simply how powerful the pump appears, it is how well the pump matches the system, the flow required, the elevation to be crossed, the resistance of the route, the control strategy, and the demand that changes through the day. A pump can work hard and still waste energy when the whole route is poorly matched. Efficiency belongs to the relationship between machine and system.
At the suction side, the pressure field can change quickly. Under local conditions, if pressure falls below the water's vapor pressure, small vapor pockets may form. As the flow reaches a region of higher pressure, those pockets can collapse. This is cavitation, a conditional event, not a diagnosis from a single picture. Repeated collapse may create noise, vibration, erosion, and lower performance in hydraulic machinery. That is why operators use sensors, protective controls, maintenance, and operating limits. The pump is not judged by bubbles alone. It is watched as a machine inside a changing system. Mira now leaves the stabilized discharge line and rises toward the storage and controlled pulse of the next episode.